Our next paper is entitled Full-parallax Spherical Light Field Display Using Mirror Array. And the speaker is Hiroaki Yano of the Nagaoka University of Technology in Japan.
Thank you for your preparation and thank you for introduction. I'm Hiroaki Yano. Let me start my presentation. Here is the outline of this presentation. Spherical 3D displays are proposed previously. The spherical displays have larger viewing zone than flat ones. The spherical 3D display enables users to observe 3D objects freely around the display. The Sphere is a spherical 3D display that employs spherical rear projection screen and head tracking system. To achieve binocular parallax, special glasses are needed to observe. Thus, it is difficult to show 3D images to multiple viewers at once. On the other hand, this projector is a volumetric 3D display. This achieves floating light points in spherical volume by rapidly rotating a circular screen. The screen displays sectional view of the displayed object. Thus, this display is capable of displaying 3D objects for multiple viewers without glasses. However, volumetric displays are not capable of providing complicated optical effects like occlusion effect or refraction. Light field display is a display that reproduces light field of the scene. This method is glassesless and occlusion capable. A typical example of this method is a century-old technology, integral imaging. The method trades spatial resolution of the pixels to directional resolution of the array. Thus, fine pixels and high-density lenses are used, and it is difficult to carve this structure to make spherical display. On the other hand, wide viewing zone light field display is achieved by rapidly rotating mirror with a vertical diffuser. This structure scan ray to 360 degrees around the display. The ray intensity is controlled by a high-speed projector. Thus, this system optically achieves horizontal parallax. Vertical parallax is achieved by viewpoint tracking. However, there is a limitation in the position of viewpoints. Here, we aim to propose a 3D display that is spherical, that allows multiple viewers to observe simultaneously without glasses. That is light field display which provides both vertical and horizontal parallax. Next, I explain the scheme of proposal system. The proposal system is light field display. Light field display should control the intensity of rays according to the position of the ray on the display and the direction of the ray. However, carving conventional display structure based on integral imaging is not easy. So we decided to use time digital multiplexing method similar to the previous work. What spherical part do is just reflect and scan ray. We employ uniaxial rotation to scan ray from the viewpoint of mechanical feasibility. This is a schematic diagram of the proposal. The proposal consists of mirror array and a high-speed projector. The mirror array rapidly rotates to scan ray. The mirrors have different angle each other to scan rays. In order to achieve full parallax, rays should be scanned in both vertical and horizontal direction. Thus, mirror's angle varies in two directions. The high-speed projector generates rays that reflect on the mirror array. The projector controls the intensity of rays by switching projected frames. Now, I explain the detailed design method of the mirror array. First, to scan rays by the uniaxial rotation of the array, the direction of each mirror aligned in rotation direction varies. Thus, the number of mirrors along the rotation axis defines the resolution of ray direction. Next, Each mirror is nearly square so that the array shape approximates a sphere. This limitation roughly defines the number of mirrors along the vertical direction from the rotation direction. The surface of mirror array is separated equally in both theta and phi in spherical coordinate. In this way, mirrors near rotation axis are small. The mirrors are not placed in the area near rotation axis. The normal direction of the mirror is distributed in the specific range from the normal vector of a sphere. Next, I explain about the creation method for the projection images. This process is based on ray tracing method. The model of the mirror array and high-speed projector are prepared at first. Then each center array of all pixels of the projected image is traced. Its position on the mirror array and reflection direction are derived. Finally, each ray color is derived by referencing 3D data of the displayed object, and the colors recorded to projection image. This process is repeatedly performed to generate a projection image for each angle of the mirror array rotation. The rotation is continuous. On the other hand, the frame change is discrete. Enough frames to follow the moving mirror is required. I will explain how the design affects the image quality. First, the refresh rate is equal to the rotation frequency of the mirror array. This is because the whole area is scanned once by a rotation. Second, the image quality is closely related to a resolution of mirror direction. Resolution of mirror direction is defined by the range of mirror array distribution and mirror number. The higher the resolution of mirror direction is, the higher the resolution of ray direction is. The accuracy of ray direction affects to the image quality and smoothness of parallax. Third, the volume of display area per array diameter is defined by scanning range of mirror. The image in the left shows ray reflection on a spherical mirror. In the proposal method, normal vectors of this spherical mirror is modulated. The middle figure shows the reflection when the scanning range is 20 degrees, and the right one shows that of 40 degrees. The display area is roughly drawn by using extended ray in the opposite direction of the reflected rays. The larger scanning range is, the larger display area is achieved. Next, we conduct computer simulations to simulate the theoretical image quality and confirm the difference among designs. Here is simulation method and parameters. We use open source ray tracing software. The proposal is based on time division multiplexing. To observe time average of the reflection, the temporary images of the moment of the mirror array rotation is generated by the software. The projection image was created by modifying the software. This shows the projection images. The mirror array diameter is 300 millimeters, and the number of mirrors is 3,000. Dice of 40 millimeters each side is displayed. This animation shows rotating mirror array. Flashing area are observed. When the rotation is enough high, what viewers observe is the time average of this animation. By moving viewpoint around the display, the full-parallax image is observed as shown in figure. However, the image is blurred and the parallax is not smooth. This is because of the discreteness of ray direction. In addition, there are black lines on the displayed image. This is because there is an area where can't reflect lights. In this simulation, we confirm the relations between the number of projection images and image quality. When the number of frames is equal to the number of mirrors along the rotation axis, we even can't identify which surface of the dice is facing. The more projection frames are used, the better image quality is. In this simulation, we identify the effect caused by the number of mirrors. A smooth parallax and better image quality are achieved by employing large number of mirrors. In this simulation, the relationship between the range of mirror swinging and image volume is identified. The whole area of display zone is colored. By enlarging swinging range, the larger volume of the display area is achieved. However, the image quality gets worse because the resolution of redirection gets worse. In the next section, we talk about prototyping and experiment. Here is the design of prototype. The refresh rate is 20 Hz and the number of projection images are 720. We formed the ball mirror by using a 3D printer, and 3,000 mirrors are placed by my hands, one after another. There were errors in the array of the mirror, angle of the mirror. The mirror direction was measured and projection image was calculated. Here we show an experimental result of the static 3D image. Looking from various directions, both vertical and horizontal parallax was observed. Compared with the first simulation, the viewing area is smaller. This is likely because of the poor accuracy of projection. When looking from the lower position of the viewing zone, the lower part of the array is used. Accurate projection on the mirrors in the lower part of the array is more difficult than projecting on the higher part of it. We observed shifts between mirrors and projection image. In addition, the image is blurred and it's not consistent in brightness. This is because the inadequate diffuseness adjustment. We also tried to display 3D animation. This animation is a rotating puzzle cube, and this is 30-frame animation. The animation displayed by the prototype is occlusion capable and full-parallax. We also developed color display based on the proposal. Normally, DMD projector employ color wheel to color display the image based on time division multiplexing. The proposal tries time division resolution to a directional resolution of ray. Thus, we employ each red, green, and blue DMD projectors to color image. However, the color of tiles are incorrectly observed. The difference of optical axis causes this phenomenon. The transition of parallax shifts between each colors. Finally, I'd like to summarize my presentation. We propose an optical system for spherical full-parallax light field 3D display using mirror array and high-speed projector. We confirmed the validity of our system by the computer simulations. The prototype was built and feasibility of proposed system is confirmed. Future work includes speeding up rendering algorithms and improving the design of the mirror array for better image quality. That's all. Thank you.